Oh, okay, let's get started. Welcome back to CS479 Machine Learning for 3D Data. As I mentioned in the last time, one of the important things that you need to know is that basically we have the deadline of the team matching. So the deadline of the project, the team matching is this Friday. So before this Friday, I'd like to ask you to form a team with at most the 3 people. And as I also mentioned last time, if you have some difficulties like finding some other teammates, you can also utilize our Slack workspace. So you can find the project, the team matching the channel, and there actually you can already see some of the other people who are basically advertising themselves. So you can join some other teams there, and you can also advertise yourself in a way to basically recruit the other teammates. So please find some other teammates. And if you also have some more other difficulties, like finding some other teammates, let us know. So then we'll also try our best in terms of like finding some other teammates for you. So what you basically need to do is basically not just like forming a team, but you also need to submit your team information in the open review. And also one thing that I also want to strongly encourage you is that basically if you do not have any kind of account in the open review, start to make your own account first. So please use your KAIST, the email, the address to make the account in the open review. So even before you form a team, in today, basically just make a account in the open review so that the other people can also basically add your name when they basically form the team. So basically, you can, if you also go to our the web page in the course with the website, if you go to the project team matching the web page, you can see what are the information basically that you need to submit. So basically, you need to submit not only the names of the teammates, but also the title of the project and some of the keywords that you are interested in. So basically, you can change the project title and also all the topics that you want to do in your project. But we also want to get what you are basically thinking as your kind of the project ideas at this time. So please basically submit the project title and also some of the keywords for your project and also all the team member information in the open review. And also there will be penalty if you do not submit this information by this Friday. So please please note that there will be some kind of a penalty if you basically pass this the deadline. And also, as I mentioned in the first week, if you consider like withdrawing this course at some time after this team matching, there might be the case that the other teammates are basically losing one of the team members. So that might be not good for the other people. So if you consider like withdrawing this course, I guess now might be the best time to do. So that's kind of like one thing. Any questions for the team matching? Actually, also speaking to the course project, you can see all the schedule about like what you will need to do. So after the team matching, you also will need to submit the project proposal, and you will also need to submit the project mockup, the outputs, and also you will need to do some project pitch. So I'm also going to explain all this the schedule next time. So that's the plan. Any questions for the course project? Is everything okay? Good. Okay, then let's move on. So if we just briefly recap the things that we discussed last time. So we were basically discussing some of the ideas in terms of like how we can do like all the conversion from the one representation to the other. So for the implicit function to the voxels and from the mesh to the point cloud, from the mesh to the multi-view images, those are basically very straightforward things in terms of doing some of the conversion. So the two kind of the missing the bridges in the conversion was these two cases, from the voxels to the mesh and from the point cloud to the implicit function. So if you can basically like connect these two bridges as well, then this means that basically we can do any kind of the conversion from the one to the other. And actually, one thing that I also didn't mention last time is that actually there can be some other ways around like doing some kind of conversion. For example, we can consider directly like converting a point cloud into a mesh, right? For example, like, so for those kind of cases, if we want to directly convert a point cloud to the mesh, there might be the case that we just need to connect the dots in the point cloud, right? can you imagine like how we can also do that? So this can be like one of the possible deconversion kind of things. So actually the thing is that like if we can also consider like making a mesh by just connecting the dots in the point cloud to make the 3D mesh. But as I also mentioned last time, if we consider like making some kind of the valid the mesh that satisfies all the constraints about the validity, like too many means all the other things, actually like directly converting the point cloud into mesh by just connecting the dots is extremely challenging the problem. Actually, there are also some ideas for that, like especially in the some mathematical forms, like in the computational geometry. You can also find some kind of the papers that tries to basically do this kind of conversion from the point cloud to a mesh. But then you realize that actually that's really complicated process, especially if you want to basically make a valid mesh. So there are lots of kind of things. So what people typically do is basically following basically this loop. So from the input function to the voxels to the mesh, from the mesh to the point cloud, that's now basically straightforward in terms of making some deconversion. And for the voxels to the mesh, actually the idea that we discussed last time was actually a very simple idea, which was called the merging squares for the 2D and the merging the cubes in the 3D. And also we could extend this idea into the tetrahedra, these structures. Then that would be the case of like the merging the tetrahedra. And here the basic idea is that we are just treating every cell in the grid independently in a way that basically if we see all the possible combinations, or like having the four corner, the points in the 2D case, whether the, seeing basically whether each of the corner point is inside or the outside of the 3D shapes, for all the possible cases, we are basically finding the points where basically we're going to have the boundary of the shapes for each of the edge of this kind of the cell. And then we are basically connecting this kind of the intersection the points in a way to basically build the edges of the meshes and also building the faces in the 3D case. Then in the 2D case, we could see that there will be like, all the 2 to the 4, the 16, the possible cases, having all the combinations of the inside and the outside, the corner points. And then we could also basically group all this kind of some sort of the equivariant cases in terms of like having some specific patterns of the connections of the intersection the points. And once we group all the equivariant cases, then we are just having the 4 groups in the 2D case, and we also could extend the same idea in the 3D. Then we're going to have the 256 cases of all the possible combinations. And after grouping all the cases, then we have these 15 groups. Then we can also apply the same idea for the 3D as well. So this was like pretty simple, the idea. Obviously, we can consider some more the complicated way, do some kind of conversion from the voxels to the mesh. But it turns out that actually this simple idea basically kind of like became some kind of standard. So for the conversion from the voxels to the mesh, like everyone is basically using this kind of the simple idea, which is quite effective in most of the cases. So which is quite good. It's quite very simple, the idea. But the conversion from the point cloud to the input function was slightly more complicated, right? So basically what we discussed last time is that we can first consider getting some kind of surface normal information. And actually the surface normal information could basically provide the more information for the surface or the volume that we want to get. So the surface normal was basically defined as kind of the normal vector of the tangent plane that we are defining for each of the point. And once we basically have the tangent plane for each of the point, we could basically easily somehow define the signed distance function. So basically also one of the ideas that we also discussed last time as kind of the idea to define the implicit function for the 3D shape or the 2D shape was basically having the signed distance the function, which was basically the case that for any kind of the query point in the either the 2D or the 3D space, we are now encoding the distance from the point, the query point, to the closest point over the surface. And we are also encoding whether the point is inside or the outside based on the sign, right? So this was kind of example that if the point is outside of the shape, then we are having the plus sign. And if the point is inside the shape, then we are having the minus sign. And then the good thing is that we're going to have some kind of the linear function from the inside to the outside in a way that, when the point has the 0 value in this function, there might be the case that the point is on the surface, right? So once we have this kind of assigned distance function, then we can extract the surface information by just taking the zero level set. Basically, zero level set means that we are taking the points that has the zero value for the given the design distance function. Actually, one also the question that we can ask is that would this be the only way that we can define the some implicit function for these 3D shapes? Would there be some other ways around to define some implicit function for these shapes? Any other ideas? Any thoughts? Yeah, neural radiance fields. Well, yeah, so we will get to the neural radiance field later. Obviously, that's kind of like one way that is not exactly define the geometry, but yeah, kind of. Yeah, so basically we can define some kind of the occupancy kind of the function in terms of that. Basically, we are having some kind of the binary numbers. So whether if the point is inside, we have the one, and if the point is the outside, then we can have the zero, or the other way around. For the points in the inside, we can have the zero, and for the points in the outside, we can have the one, right? So occupancy function might be the other way around to define the implicit function. So there can be actually multiple ways to define the implicit function for these 3D shapes. And we are also going to get into this kind of the cases in the later the lectures. Cool. So basically what we wanted to do last time was that given a point cloud, basically we wanted to basically recover this kind of the some implicit function, either the sign distance function or the implicit function. So let's get into the case of the sign distance function. For those kind of cases, so we could consider like three different kind of approaches to recover the implicit function. The simplest idea was basically given for a point, we are just finding the closest point in the given the point cloud and measuring the distance to the tangent plane. So that was kind of the simplest idea. And we also could extend this idea by just like not just only finding one single point, but considering all the points that we are having in the point cloud with some kind of the weights. The weights will be basically defined based on the distance from the quarry point to the other points. So that can be basically the idea, which was basically also called the moving least squares, which could be actually interpreted as kind of the local the kernel regression the idea. But actually, the better idea might be is that we are doing some kind of the global sort of the kind of optimization, not only considering some kind of local points with some kind of the weights, but we really consider the entire set of the points and also there the normal information in a way to recover all the surface information. So that was the idea that we are basically rushing last time at the very last review means. So I'm going to get into this idea a little bit more, like in a way that so how we can exactly basically do some kind of the global optimization. So basically what we also observed last time is that given any kind of the implicit function that actually we want to recover from the given set of the points, what we actually could see was that the gradient of the implicit function actually is basically the surface normal information. So that's kind of the fact that we are going to utilize here. So given any kind of a set of the points and there the surface normal information, what we could see is that the surface normal information should be basically the same with the gradient of the implicit function. So that's basically kind of the basic idea. Then what we are going to do is that given a set of the kind of the points and they're basically the normal information that basically provides some kind of the vector field in the space. So given a kind of given the derivatives of the function, we want to basically recover the original function in a way that if we take the gradient of the output the function, the gradient of this function becomes the gradients that we are having. So that's basically what we want to do. So which means that if we have any kind of the vector field that basically represent the derivative of the function that we want to get, if we can take the integral of the vector field, then we can directly recover the original function we want to get. So that's basically basic idea. But here basically the one problem is that for most of the cases for the vector fields that we are getting, the vector field may not be integrable. because there are some kind of certain conditions that should be satisfied if we want to directly take the integral of the vector field. So basically, the given the vector field should be conservative if we want to get the integral. So which are basically the cases that the given the vector field basically like satisfies all this kind of the constraints. But for most of the cases, especially in the case that we have some kind of some small noise in the surface normal that we are having, the given the vector field may not be integrable. So that's kind of the problem. So that's basically why we want to solve this problem, not in a way to basically take the integral of the vector field, but in a way to basically find a function that basically best approximates the given the gradients. So we are basically finding a function f here, which is basically minimizing this kind of the mean squared error. So basically, when you take the the gradient of the function we want to get, we want to basically minimize this difference. So we are basically getting the final of the function the f in a way to basically minimizing this difference between the gradient of the function they want to get and also the input, the gradients. So that's basically the formulation that we want to solve. So in the 1D case, basically we're gonna have this kind of the formulation that you can see at in the bottom. So this is basically the formulation that we want to solve. Then basically the question is that how we can solve this problem, right? So if we get into slightly more the details about that, like especially in the 1D case. So we're gonna first go into the like all the 1D case first, then we're gonna see like how this can be extended to the multi-dimensional space. But in the 1D case, if we see how we can solve this formulation quickly, is that basically if we have any kind of the function like this, a function L, which is defined with the x and the function of the x, and also the first derivative of the function of the x. For those kind of cases, this stationary points, basically either the minimum points and the maximum points of this kind of the function can be basically obtained as the solution of this PDE. So this is kind of the known fact as kind of the Euler-Lagrange equation. So basically, in our case, what we can see is that what will be kind of the L in our case, right? So basically, the L function in our case is basically this mean squared error here. So the thing is that given this kind of the L function, which is defined as kind of the mean squared error, if we plug this in into this PD, then what we can get. So that's basically the things that we can do, as you can see in this derivation. We don't need to get into all the details here. But what we end up getting after like deriving all the things is that the solution for the minimizing the mean squared error is basically finding a function which second derivative becomes the same with the first derivative, given the input, the function. So this G is basically the given information, which is given the first derivative, the information for the function we want to get. Then the solution of the mean squared error, minimizing the mean squared error, is the case that we are finding a function which is second derivative basically becomes the same with the first derivative of the given the function. And in the multi-dimensional case, basically the solution for this becomes like this. So given any kind of vector field, we want to find a basically function f, which Laplacian becomes the same with the divergence of the given vector field. So basically in the multi-dimensional case, the Laplacian basically the rule is the second derivative, and the divergence plays the role basically the first derivative, the kind of the case. So as you can see, basically what we need to do, basically in a way to basically solve the global optimization problem is basically solving this equation. And this kind of the equation that looks like this is called the Poisson equation. So that's why this technique is called the Poisson surface reconstruction. It is clear? So this is basically what we were going to do. And then the question is that basically how we can calculate this, kind of in the discrete setup, because we basically want to get all this kind of the information in some kind of some discrete setup with some kind of the grid. So basically in the 1D case, that what we can do is that basically all the function. So let's think about that. The vector field is also kind of some of the function, given function here. And also we want to basically recover this function, right? So basically, the function f here in the discrete case, actually can be represented as a vector, right? So basically, if you have any kind of 1D space, and if you have some kind of the samples with the uniformly interval, then you're gonna get the value of the function for each of the points, right? Like for like the x0 to the x1 to da 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 da, then you're gonna have the fx0 and the fx1s. So which means that we can also discretize the given function like this. So in this way, any kind of function f can be actually represented as a vector in the discrete setup. So this is very straightforward, right? And also then the question is that given this kind of the discrete representation of the function, how we can calculate the gradient, right? Can you see like how we can calculate the gradient with this kind of the given the vector representation of the function? Second question. So here basically the thing is that the function f itself will be represented as a vector, right? And also the first derivative of the function will be able to be also represented as another vector as well, right? So, I mean, there can be some multiple ways for this, but basically we can also define the gradient function like this. So in this kind of discrete setup, if we basically have any kind of the input function, which is represented as a vector like this, given this kind of like uniform interval of the samples, with interval dh, the first derivative can be basically approximated like this, right? Taking the two consecutive values and basically taking the difference between these two and dividing this by the the interval between the two, basically the samples. I mean, there can be some multiple, like slightly different versions of this. So this can be basically one way that we can define some kind of the gradient, the operation, right? And this will basically the case that we are having a operation of the gradient, which is basically mapping the function f represented as a vector to the basically the a vector, which is also representing the gradient of the function. Actually, and also then what we can see is that actually the whole the gradient of the operation actually can be represented as the matrix like this. So given any kind of the function, the f like this, we can define a gradient function in a way that if you basically multiply like a times the f like this, then that becomes the vector of representing the first derivative like this, right? It is clear. And also the good thing is that this operation, the gradient operation represented as a matrix can be predefined given any kind of the 1D, 2D, 3D grid that we are having, right? So given any function and also the predefined the gradient operation represented as kind of the matrix, we can now basically compute the gradient of the given function as kind of the matrix demultiplication. So that's kind of thing. So in the continuous space, we are basically having a function f, and also the gradient, the operator, which is basically playing the role of converting the given function into the function of the first derivative. And then this mapping function, the gradient operator, now can be represented as kind of the matrix in the discrete form in a way that we can compute the gradient as the matrix multiplication like this. So this is quite straightforward, and this is the same for the second derivative as well. Like even also when you have the second derivative, it's exactly the same. We can also define another the operator, which is the second derivative. Then that is also mapped to the one of the kind of the matrix form like this. And then basically by multiplying the function f with the Laplacian the matrix, basically the second derivative the matrix, we can get the second derivative the function of the given function. Then as you can see in the previous slide, so let me go back to here. So what we wanted to do was basically solving this, right? So this means that we will be able to basically define a kind of the matrix for this Laplacian the operation. And also we will be able to define some kind of a matrix for this kind of divergent operation. Then what we need to do is basically doing some kind of the matrix multiplication for the V. So basically computing the divergence of the given the vector field. And this Laplacian is represented as kind of the matrix. Then this will be basically the case of like solving this kind of the least security problem. right? So given the A and the B, what will be kind of the X that we want to get? So this will be basically very simple, the least security problems that you can see in the linear algebra, but we're also not going to get into any details here. So yeah, so basically this is what we are going to do. Given the matrix defining this like Laplacian the operator, and also given the other the matrix defining the first derivative the operator, and also the given function g, which is like is given from the surface normal information, we are solving this least security problem in a way to get the f. So that's basically what we want to do in the 1D case, and this can be also extended for the multi-dimensional space. Here, one important question is that so when you have this kind of the equation, would the solution unique? Actually, the answer is no. Actually, I just put the answer here. The thing is that while this kind of the Laplacian matrix can be defined as kind of the security matrix, we can get the unique solution of the f when this Laplacian matrix is basically the full length matrix, right? But it turns out that actually this Laplacian matrix is not full rank. But if the scale, the size of the matrix was the m by n, actually the rank will be m minus 1. Can you guess why? Why the rank, or why is the rank of the Laplacian matrix it's not full rank? Which means that why is it not possible to get some kind of unique solution for this? Yes, boundary values. So actually, you can guess the answer for this without having any knowledge about like linear algebra or something, right? If you think about like what's the meaning of like taking this operation, like this is basically the case that we are taking the second derivative, right? Especially in the 1D case. This can be considered as like taking as kind of a second derivative, even for the first derivative as well. Actually, the thing we can see is that, like, think about the case, like we are having the function like y equals dx. Right? And we also have another function that we are adding some kind of the offset to this function, right? If we take the derivatives of these two functions, we can see that the derivatives should be exactly the same, right? So basically, whether we add any kind of the offset into any function, clean this up. So when you have any function, however we basically add any kind of offset to this function, the derivatives are not changed because this will appear after taking the derivatives, right? So whether you have like function like this or function like this, like let's say like these two are exactly the same function, except for that we are just adding some kind of offset, right? So now how much the offset you add, basically, given any kind of function, how much the offset you add, basically the derivatives will not be changed. So that's basically why we cannot basically specify the function here. Why basically there's no unique solution for this equation. But that this also means that if we can fix like only one single point in the space, even when you can basically fix any kind of like at least like one single point in the space, then based on basically this fixed point, now we can specify this function. So which means that we just need like at least like one the condition, right? To basically uniquely like basically specify the solution of like this equation. So it's up to you. So you can basically choose this kind of like the boundary condition. You can basically set any kind of the points to be empty or occupied. And also, these are basically the case that we are basically missing, not using some of the information. So this was basically the formulation that was basically derived with the surface normal information, right? which is basically the first derivative information of the implicit function that we are getting. But actually, we have some more information than the surface normal. What's the information that we are not using here? Anyone? So actually, we are only using the surface normal information here, but actually we had some more information. Yes, so that's the answer. So basically, what we can see is that, like, given the given set of the points, we are now taking, the normal information, the surface normal information for each of the points, in a way that, the surface the normal the vector becomes the first derivative of the given the output, the implicit function. But actually, obviously, what we can use that, we also know that at these points, at these locations, the impulse function, especially the sign distance function, should be 0, right? So that's also the information that we can utilize for all the points that we are having in the given the point cloud. Actually, we can add the constraint that the function, the sign distance function at this point should be 0, right? By definition of the sign distance function. So that's basically also the function that we want to get. So we are basically getting the a function which becomes 0 at the points that we are having in the point cloud, and also the derivative of the function becomes the surface normal, right? But actually, this was the equation that we are only using the surface normal information, not the points itself, the point coordinates itself, right? So we can basically formulate the problem like this. So we are basically adding this term in a way that we are not only basically minimizing these mean squared errors for the first derivatives, but we also minimize this in a way that the function, the value for the given the set of the points also becomes to be minimized. So this can be also added as some kind of some sort of the regularization in the entire the minimization of the problem. It is clear. One kind of the interesting defect is that like this looks quite obvious, like adding this term here, but it's basically the idea of like adding this term was like first introduced in the 2013, while the first idea of like the pure the Poisson surface reconstruction was introduced in the 2006. So it actually took like 7 years to add this like small regular, very obvious deregulation term. This is kind of the comparison between the two cases. So these are also the cases that given the point cloud was very dense. So we can actually see quite good results, like recovering all the surface with some all the fine details like this. But actually, if you see the very much details here, what you can see is that given this kind of a set of the points, with some noise like this, if you just use the original the Poisson the surface reconstruction without using the point the coordinate information, then you are getting this red curve, which is not perfectly aligned with the given the set of the points. While if you use this kind of the additional the constraints, it's kind of the regularization, then now you're getting these results, which is basically better aligned with the given set of the points. So these kind of things are basically additionally the information that we can utilize when solving the Poisson equation. Is this clear? So this summation equals to 0. We are basically minimizing this. So we are finding a function in a way that the function value at all these basically the points to be basically 0. So basically, in the previous the Poisson surface reconstruction, this information was not used. So without this information, basically we minimize the difference between the first derivatives of the given information and the output information with some kind of the additional the boundary in the condition. But actually, we could consider basically adding these constraints in a way that the function value should be also 0 at the given set of the points. Just adding one more term here. Is this clear? Cool. So this is like very simple things. Obviously, this is simple in the 1D case, but as we go into the higher dimensional space, it might be basically slightly more complicated in a way to that we basically need to define the matrix form of this Laplacian the operation and also the divergence the operation. So in the 2D or 3D case, we can basically define the matrix form of the Laplacian and the divergence, and we can also do the same kind of things. So we are not gonna get into all the details here because we ran out of time. But basically, here some basically the take home the message is that we can basically consider like solving the Poisson equation in a discrete space in a way to basically see the continuous function as kind of the discrete vector in the discrete setup, and also convert the continuous operator like the Laplacian the divergence into the discrete matrix. Then all this kind of the composition will be basically seen as kind of the matrix demultiplication, and also like solving all of the Lagrange the formulation will basically become the solving the least scarcity problems, linear least scarcity problem, which becomes like very simple kind of things in terms of that we can directly just solve the equation. So some kind of the details, actually there are tons of some details in terms of like how we can exactly implement all the things, but we're gonna skip some details here. But basically the idea in terms of the implementation will be is that why is it considered as an variational form? Actually, I also couldn't get the question. Why is it? Or can you elaborate the question? Can you just like speak up?
Yeah, sure. You have a text saying a continuous variational problem can be approximated by a discrete one.
Yeah.
I was wondering why it's a variational problem.
So, why do we solve this as kind of like discrete problem, or?
Why is it a variational problem in the beginning? I think I don't get the meaning of variational in this case. Like, yeah.
Well, I mean, basically, if we, sorry, I still couldn't get near the question. So basically, if we basically, want to basically get this implicit function from the given information, then that's basically what we get. Like given the first derivative information, we are basically solving like this equation.
Okay.
Would there be some other way around? So like, what is the point of that question?
I just don't understand the meaning of variational in that case. The word variational.
Where? Where did I say it?
A continuous variational problem.
Yeah, I mean, so basically,
It's okay.
yeah. So we basically wanted to basically the continuously form of the function. But basically, we also need to represent the function in some ways, right? So the way that we want to basically represent the continuous function is basically getting the boxes again. Then we're gonna basically get all the values for each of these cell in the given degree. So that's basically what we are going to do.
Thank you.
Basically, given like this any kind of a 2D or the 3D grid, so basically what we are going to do is that we want to basically populate all the vector fields of the surface normals that we are getting for each of the cell in the grid. And then basically given this kind of the vector field over the space, we are first computing the divergence with some kind of the predefined divergence operator represented as the matrix. And then also with some kind of the predefined the matrix of the Laplacian, we can now directly solve the Poisson equation. And then based on that, now this will be the case that now we are having some kind of the voxel representation, which means that for each of the cell in the grid, we're gonna get some kind of the value of the function, which means that now we can directly apply some kind of the marching cube kind of the idea in terms of like extracting the final mesh. So that will be basically some of the ideas that that we can apply. Any questions on this? Yeah, so basically we are getting the implicit function, and we also basically need to apply the optimization over the function. So that's the idea. Is this clear? Any questions? No? Yeah, so this was basically the basic thing of the problem, the surface reconstruction. And here, basically, one of the messages that I wanted to say is that, like, for those kind of the problems, like converting a point cloud into an implicit function, some of you might also thought that actually, yeah, this might be a problem that we might need to use the neural net. But it turns out actually without the neural net, actually we can do this kind of the optimization to recover the function, right? So if you have any kind of the set of the points and also the normal information, by utilizing all these kind of things, we can directly just solve the Poisson's the equation to get the implicit function. So this is actually the problem that we can basically directly solve without doing some kind of the prediction using the neural net. So that's also quite important part in this course. So basically for this kind of for all the problems, actually we need to see what are the problems that we really need to use do some kind of the prediction using the neural net, where we can directly estimate the final outputs in some kind of the optimization form in a way to minimize some kind of the energy, right? Some kind of loss function. So also in the neural net training, we are defining some kind of a loss function, right? But the difference between like minimizing the loss function in the neural net training and solving this kind of optimization, the problem is that here in this problem, we don't need to basically involve any kind of the training data. So if you actually see some kind of the prediction, the problems in these many neural net based kind of things is that those are the cases that we are defining the loss function with some kind of the training data. For example, like some classification, right? For the classification, we need to basically check whether the output, the classes, that the scores for the classes that we are getting are basically aligned with the ground truth, the given correct the answers for the classes, right? The labels, which means that the loss function will be basically defined with some kind of the correct answers for the things that we want to get. But in the test time, we don't have the access to this kind of the ground truth, the correct answer, the information, right? So that's why basically we need to do some kind of the prediction without having any kind of the ground truth. How we can basically do some kind of the to get some final the outputs in a case that we cannot actually minimize the loss function. But this is the case that we can directly basically minimize the least scarce, right? So this is basically optimization the problem that basically some kind of loss function in this case is defined without the training data. So for those kind of the cases, actually we don't need to utilize any kind of neural net. So that's kind of like main message. If you basically consider that neural net is kind of solution for everything, actually there are lots of the cases that we can solve the problem without the neural net. So that's also kind of very important thing. And also one thing that I wanted to basically mention here was basically that this Poisson's equation actually can be seen in lots of the applications, not only for this kind of surface reconstruction, especially in the computer vision and the graphics domain. Actually, you can find that actually there are lots of the kind of the tasks that actually we can directly utilize this kind of the Poisson's equation in order to solve the problem without the neural net. So that's also some of this is kind of like very old kind of example from like the paper, like 20 years old. So this is kind of the example that we want to take some kind of the foreground object here and also another the foreground object here in a way that we want to composite these two objects into this background, right? So if you directly take this dog part, and these like the keys here. And if we directly copy the foreground region into the background image here, then you're gonna see this. This is nothing but just directly cropping these two the region for the objects and copying them into this background image. Actually, we want to get this kind of the seamless the outputs. So now we cannot see any kind of the boundary of the foreground and the background, and we can see that like these two the foreground the objects are basically seamlessly attached over the background image, right? And this is also the same example, like also basically doing some kind of the manipulation of the images, basically taking some foreground region and just copying them into some background image, right? So how can you do this? Can you imagine like how we can do this without the neural net, but by just solving the Poisson's equation? Another question. How we can also solve this problem using the same Poisson's equation? Yes, that's basically what we want to do. Yeah, so you don't need to just like copy someone else's answer and think about your own idea. So basically what we can do is pretty simple, like, so given the foreground region from the other image, actually we are not copying the colors, but actually we are copying the gradient of the colors. So what we can do is that in the background image, like we were basically filling this region in a way that we match the gradient of the colors here with the gradient of the given the foreground image. So this basically means that we are not taking the color information here, but actually we are taking the gradient of the color information in the foreground region with the boundary condition. So we basically set the colors on the boundary of this region to be exactly the same with the color of the background image, while basically we are filling the inside region basically in a way that the gradient of this region to be the same with the gradient of the input image. So that's basic idea. So this is nothing but exactly the same kind of the equation in a way that we basically match the gradients of the output function with the gradient of the input the image, while basically fixing the colors on the boundary here with the background image. So this is basically nothing but exactly the same. So using the same Poisson's equation for some kind of image editing setup. And surprisingly, by just solving this simple least scarce the problem, we can get these kind of the results. So these were basically some kind of image editing the examples that we could see 20 years ago without the neural net. So this is like one of the examples that there are lots of kind of the cases we can basically do some kind of the image editing and also the shape editing without the neural net. So this can be also kind of one of the good examples for this. And you can also say that this Poisson's equation can be used in the lots of the applications. So these two are basically some of the examples like using the Poisson's equation. But there can be actually lots of the other kind of the some applications for those. Okay. So this was the basic idea for the Poisson surface reconstruction. And also we discussed the two more the ideas about like moving least scarce and the simplicity idea of like getting all the implicit function from the point cloud and the surface normal information. Can you still see what we kind of the the limitations of the Poisson the surface reconstruction? What are the limitations of the Poisson surface reconstruction? Can you guess? Question? Not learned? Well, not learned is not a limitation. Actually, it's good because you don't need to train any kind of neural net, right? Difficult to compute. Well, actually, it's just like solving least scarcity problem, right? So once you can basically define the matrix form of the Laplacian and the divergence, and this is nothing but solving some least scarcity problem. There are tons of the code for that. Heavy computation, yeah, the heavy computation can be like one of the issues, but actually there are also lots of the techniques, like how we basically, boost up the computation, like all the things. So that's kind of the one of the missing things that I didn't explain. But actually there are some kind of technique to make some kind of the adaptive, the grid, the cells in a way to basically ignore some of the kind of the cells in the empty space. Actually, there are kind of some of the limitations. Obviously, this Poisson surface reconstruction works quite well in the case that when you have some kind of the very dense point cloud without some kind of the noise and the outliers. Right? So if the point cloud is like sufficiently the dense, and also if we can get quite accurate and also the consistent normal information, then this Poisson surface reconstruction will work quite well. Yeah, so that's why people are using this technique for many kind of cases. But the thing is that basically we need to get the surface normal information, right? And also we have seen some kind of the ideas in terms of how we get the surface normal information. But in any case, since we are also getting the surface normal information from the given the point cloud, the normal information that we are getting may not be basically the accurate, right? And also, as I also mentioned in the last time, actually we also need to make all the surface normal to be the consistent over the points, which means that if the normal direction is like this, and for the other points, if the normal direction is like this, and then this will be basically the case that the sign is the distance for those 2 points are basically also the flipping the signs. So this will also basically result in the case that we are having some kind of the like boundary like this. So which means that we also need to orient all the surface normal in like the consistent way, which is not that kind of the straightforward task. So that's kind of like one thing. So we need to have the very accurate and also the consistent normal information. Like getting this information also is not that easy thing, especially when the point cloud is not dense enough. So which also means that we also need to have some kind of the sufficiently dense the point cloud. So that's kind of also one thing. Also, if we think about some kind of the cases, like lots of the cases, we are getting the point cloud from the scan, like from the 3D scanning, then also the 3D scans might involve some lots of the kind of noise and the outliers. And as we have some more kind of the noise and the outliers in the point cloud, we're gonna get also the inaccurate the normal information or inconsistent normal information, which all result in some kind of the bad output in the final the results. So that's will be kind of the limitations of like using the this kind of the idea. So that's kind of the limitation. So actually there are, so to like overcome these kind of the challenges, we can actually consider using the neural net. So that's kind of the interesting parts, but we are not gonna get into all the details here. But basically one thing that I just prepared here is that also this is kind of sort of the off-topic things, but so also quite interesting thing is that actually there are also lots of the techniques in terms of like boosting up this like the solving this Poisson's equation. Actually here the basic idea is that we could say that like solving this equation is basically solving the least scarcity problem, right? Which might still take some kind of time. But it turns out actually if we utilize some kind of the spectral method, like taking the Fourier transform with all the functions, and if we actually try to solve the same problem in the spectral domain, and it turns out that like solving the problem becomes not like solving the least scarce, but just doing some kind of the element-wise multiplication. So basically, solving this problem becomes like much faster in the spectral domain. So actually, there is kind of the one idea in terms like solving this Poisson's equation in real time in GPU in a way that now we can also optimize all the positions of the points and also the surface normal information in a way that once we basically optimize and the points and the normal information, when we basically convert this point cloud into the implicit function, the indicator function here becomes the ideal function that we want to get. So in the case that when you have the ground truth, for the indicator function. And so given some kind of the input point cloud with some kind of the noise, both in the coordinates and also the surface normal information, we can consider basically running the Poisson surface reconstruction in real time in a way that we can now optimize also all the positions and the normal information of the points like this. So this was kind of like one interesting case, like solving the Poisson's equation in real time in spectral domain, basically to update the surface normal information and also the points information. And also there are lots of kind of the work in terms like in the case like when we cannot get some kind of the accurate the surface normal information, how we can directly convert the point cloud into the implicit function using the neural net. So there are also kind of the neural ideas utilizing some neural network for this kind of conversion. In the case that when the points are like very noisy like this, or like not dense enough, like for those kind of cases, how we can directly basically convert the point cloud into the implicit function using the neural net. So those are also, that's a sort of kind of the interesting ideas for that. But we are not going to get into the like details of this. What's the question? Why is it that this problem is faster in the free domain? Because like in the spatial domain, basically you need to solve the least scarcity problem, which has some like very, basically some kind of complexity for that. But like solving the least scarce in the spectral domain just becomes basically doing some kind of the element-wise demultiplication, so which becomes like way faster. But actually also there's some kind of the cost for the Fourier transform. Basically, we will need to do some like Fourier transform and also the inverse Fourier transform. So we are taking the cost of like this conversion, but once you convert all the things into the spectral domain, then like solving the least scarce basically becomes the least scarce, doing some kind of the element-wise demultiplication. So if you are interested in some more details, you can check out this paper and see some details here. Yeah, it'd be interesting to get into some details here, but I guess it might be too much for this. Any questions? Yeah. So actually, the main topic that we need to discuss today was not this. So let me reshare my screen. So yeah. So we are a little bit like behind the schedule. So actually, the main topic that we wanted to discuss was basically the point cloud encoders. So what we have seen is that, yeah, there are lots of the multiple the representations of the 3D data. So we also have seen like how we can basically convert like one to the other. Then let's think about some kind of the main things in terms of, so how are we gonna basically process all this kind of like some geometric the 3D data for some kind of the tasks, and how we can basically define a neural network that can process this kind of 3D data. And the things that we are going to discuss actually today is basically some kind of the network that can take the some 3D data as the input. Especially we are going to see some kind of the techniques that can take the point cloud as the input. As I also mentioned in the last week, actually we can also consider some other kind of architectures that can take the 3D voxels as the input. Then we can directly just use the some kind of 3D convolution to neural net or some kind of transformer kind of things. But we can consider applying some kind of 3D convolution in the voxel space. And as I mentioned last time, which will basically take lots of the cost and also the computation, the time and the memory. And also we can consider a kind of the architecture that take the mesh as the input, like the mesh net we also discussed the last time, using some kind of some special pulling the operation, but they may not be generalizable that well into some kind of the arbitrary mesh structures. So we are going to basically consider some kind of architecture that can take the point cloud as the input. Then the question might be is that why do we consider a kind of architecture that takes the point cloud as the input? Well, actually, one of the advantages when you can make some kind of the architectures that can encode the point cloud is that actually many kind of the data, some 3D data that we can see in many kind of application is basically the scan data, right? So basically, we can basically have some kind of the other types of the 3D data, like some kind of the 3D CAD models that we can see in some kind of the online repositories. But for so many other kind of some applications, some kind of the task that we can expect to see, some kind in the autonomously driving, like just having the LiDAR sensors, like scanning the all the environment, and we want to detect some kind of all the moving vehicles or the pedestrians, like all those kind of the cases. For those kind of the applications, the input that we are getting would be basically having some kind of scan data, which would be the case that we are having the point cloud, right? And also for many kind of some robotics applications that we want to basically teach the autonomous the agent to navigate in the space. For those kind of the cases, basically the robot basically need to basically scan the scenes. And this will be also the case that we are taking the point cloud as the input, right? So for those kind of cases, if we have some kind of the point cloud encoder that can basically directly process, take the point cloud as the input, then we can basically utilize all this kind of data without doing any kind of conversion, right? So that's quite convenient because we don't need to do any kind of the pre-processing. And also, as you can see in this kind of the pipeline that we have seen in the previous slide, actually it's quite easy to convert from the implicit function into the point cloud. So if we see this sequence, like basically having the implicit function to the voxels is straightforward. And from the voxel to the mesh is just running the marching cubes. And from the mesh to the point cloud, it's just like sampling the points, right? So this way, basically the conversion is very simple. There's nothing complicated. But as we just have seen in the previous the slides is that like the point cloud, the conversion from the point cloud to all the other representation is not that straightforward. I mean, basically we need to have some dense point cloud, and also the point cloud need to basically noise free, and also we should be able to get the accurate surface normal information. So we can try to convert the point cloud into the other representation, but in most of the cases, it may not be that easy to get some very accurate the outputs, especially in the case that when you have some kind of the noise into the point cloud, and also when the resolution of the point cloud is basically not that high, which means that by basically converting from the other representation to the point cloud is quite easy, but the conversion from the point cloud to the other representation is not that easy. So basically, if we have basically a neural network that can take the point cloud as input, that might be quite convenient in a way that whatever representation you have, you can basically sample, basically convert everything into the mesh and just sample the points, basically getting some kind of the point cloud representation for any 3D data that we can directly utilize this kind of the point cloud encoder. So that's basically the case that we want to get have this kind of the point cloud encoders. What's the question? Even the shape as points, it's not accurate. Well, I mean, yeah, even using this kind of the shape as the points kind of technique, there's also the idea there is basically just like boosting up the Poisson the surface reconstruction. But still, if we want to get the accurate the points and the normal information, we need to have some kind of the ground truth information for training. So that's basically, yeah, the special case. So that's the basic idea. So the point cloud representation is kind of the best representation in a way that we can convert from any other representation to the point cloud very easily. But the other way around is not that easy. So that's basically one of the reasons like why you want to basically have some the point cloud encoders. And also this means that if we can have the mesh as the input or some other input function as the kind of the data that we have, then we don't need to use the point cloud encoder. As I said, actually, it can be better to use some kind of the 3D the convolution of the neural net, especially the sparse convolution neural net, just like some kind of efficient implementation with the 3D convolution, where you can basically also consider like rendering the mesh into the multiple images and using the 2D convolution neural net or some image transformer. So that can be actually more effective in terms of like, especially in terms of like improving the accuracy of the final the tasks. But for many other the cases, basically, if we have the point cloud encoder, that might be quite convenient in terms of that you can easily convert everything to the point cloud. I wonder what is the significant difference between the voxels and the point cloud? Why don't we just treat the central voxels as points in the cloud? Well, I mean, actually, the voxels are basically having the volume information. For every the voxel, we are having the information about like whether this voxel is included or not, right? The point cloud is just having the surface information. We are just only having the points sampled over the surface. I mean, it is clear. Cool. So that's kind of the reason that why we want to say the point cloud encoder. Okay. 10 minutes. But basically, also as we have seen in the previous lecture, kind of the downside of the point cloud is that, well, I mean, that can be kind of, so yeah, for now, we are not going to consider like, whether this can be applied some kind of the applications for the rendering or the manipulation. So we are only, for now, we are only interested in kind of like making a neural net that can take the point cloud as the input. But then the problem might be is that like some kind of the old idea that we can see in the many neural network is basically having some convolution of the operation, right? Having the convolution of the neural net. But the thing is that the point cloud is not that the regular structural the kind of representation, which means that we won't be able to directly apply some kind of the idea of the convolution of the neural net. So here the main question for the point cloud is basically how are we going to handle this kind of the irregularity of the data, in a way that we are designing some kind of architectures. And we will see that actually very simple, the idea of this kind of handling the point cloud is actually quite effective in most of the cases. And obviously there are lots of the ideas in terms of like making some more complicated version of the architectures. That's what we are going to see. Some structure, what sort of structures you need for the boxes? The structure is basically some volume information, right? It's either when you have some occupancy grade or the sign distance d values, we are basically seeing not only the surface of the points, but also seeing that what are basically the points that should be inside and what points that should be the outside, right? And from the point cloud, we want to recover this kind of the sort of volume information using the surface number, the information. It is clear? Any questions on this? Cool. So actually also the thing is that this idea of the point net, this is also things that you will need to, you will basically see in the first assignment. The first assignment will be basically about like implementing a part of the point net in a way to basically doing some like doing some kind of 3 tasks. Like one is the like classification, and the other one is the segmentation, and the third one will be basically making a autoencoder. So that's basically what we are going to do in the first assignment. Okay, so I don't have enough time to go over into all the things for the point net, but let's see. So basically the problem definition is that we are having a set of the points, right? So let's say the set of the points can be represented as kind of like 2D gray, the array. Like we are having the m by 3 kind of the matrix. So let's say in the 3D space, we are having the x, y, z, the coordinates for each of the point. Then we're going to have basically like this kind of like m by 3, the 2D array, right? So given this kind of like a point cloud, we want to basically solve some multiple problems like classification or the part segmentation or some kind of semantic segmentation. So here basically what we can see is that classification is the case that we are basically getting some like kind of the one number for the entire shape, right? So basically the class of the object is basically the global information for the entire shape. So this might be the case that we are getting like one single number for the entire shape. And the segmentation is basically the case that we want to get the same kind of class kind of the information, but not for the entire shape, but for each of the points, right? So the classification would be the case that we want to get the per shape the information, and the segmentation would be the case that we want to get the per point information, right? So this would be the case that when you have any kind of the m by 3 the matrix that we are taking as kind of input, the classification might be the case that we are just getting the like one single number, right? And the segmentation might be the case that we are getting the some kind of numbers for, sorry, oh shoot, by 3. Yeah, the segmentation might be the case that we are getting some kind of numbers for each of the point. PowerPoint information. How do we play semantics? They're mapping from the class labels to the class labels. Like class labels. Well, I mean, yeah, for the semantic segmentation, typically we assume that we have the given information for the class of the objects. Yeah. So Yes, for those kind of the part segment, yeah, that can be also the case. Then, or the other way around is that, especially for this kind of the part segmentation, we are just basically aggregating all the part labels for the every class. So if we have like n, like actually that's what we are going to see in the later this slide. So basically, if we have like 16 classes of the shapes, then for each class of the object, you're gonna have some kind of the part labels, right? Then you can basically aggregate all the part labels for the across all the classes, and then you can basically try to basically assign one of the label to each of the parts. So that can be one thing. While the other way around might be is that you first basically classify the object and then basically get the part label with that class of the object. So that's also the other thing. Any other questions? Also, basically the thing is that so in parts that you could have learned this, I mean, it's possible. So it also depends on like how we implement all the things. Either if we basically aggregate all the part labels across the different the classes, then we might see some kind of the failure cases that we're having some kind of the like mixing some part labels from the different classes. And if we want to avoid this kind of like the failure cases, then we can first basically classify the given the object using some kind of the classification, the network, and then we can basically assign the part label for that specific class of the objects, right? How does the labeling segmentation task work? Actually, that's what we are going to discuss in this lecture. Yeah. So we want to basically assign some kind of the score for each of the part label for each of the point. So then here the question is that how we can make a kind of neural network that can basically give us some kind of the per point information, right? So point cloud use the homogeneous coordinates and the representative. No, we don't need to use any kind of the homogeneous coordinates here. Yeah, I mean, if we want to do some kind of some transformation, then we can consider like using the homogeneous coordinates, but here no. We can just take the x, y, z information. And also the thing is that we can take not only the XYZ information, but actually we can use some kind of extra information. For example, if we have not only the coordinates, but some kind of color information like the RGB, or if we either also have some kind of numeral information like NX, like NY and NZ, then we can basically take this kind of like 9-dimensional vector instead of the 3-dimensional vector for each of the points. So that's kind of one thing. Hierarchy between class and the parts of the class. Do we know that the wing goes to the L plane? Typically, yeah, we gonna have this kind of some relationship. Also, it depends on how you define the part labels, right? It all depends on how you define the labels. But if for many kind of some typical the benchmarks that we're gonna see, obviously the part labels are defined based on the class of the objects. So each class of the objects is basically having a set of the part labels. So we can consider basically aggregating all the part labels and just like solving like one segmentation problem, where we can first classify each of the objects and run the segmentation. Okay. Any questions? Yeah, I guess we are running out of time to discuss some details for the point in it. But basically, yeah, yeah, we will, I guess, need to continue discussing these things next week. But the thing is that even before we discuss all the things, you will basically need to take a look at some kind of the ideas of the point net, and we will need to start to implement the point net. So that's basically the things that we need to do. So one thing that I want to also say as kind of the final remark for the point net is that this is basically very general the architecture that can be used not only for the classification or the segmentation, but for the many other tasks. Because basically what we are going to do is that we are making a neural net architecture, which is taking the n by 3 or n by k. I mean, it can be like, not only just like 3, but having some kind of the extra information. Having this kind of 2D array and making the two architectures, like one architecture is just like giving like some kind of the global information for the entire point cloud, while the other architecture is basically giving us some kind of like per point information. So basically, it's just a matter of like making two architectures. Like one is basically giving the per shape information, and the other one is basically giving us like some per point information. Actually, there can be tons of some kind of the problems that are basically having the same form. Do you have any kind of some guess, like what would be kind of the problems that we can utilize these kind of architectures? Last question. Either for those of kind of the two cases. Like if we have any kind of neural net that takes the point cloud as the input, actually it cannot be used the generation. Generation is not the case that the point cloud is taking point cloud as the input, but actually making the point cloud as the output, right? Yeah, actually normal vector estimation is actually one of the examples. Like if we want to utilize the neural net for the normal vector estimation, then we can use the second architecture because the normal vector is basically the per point information, right? Pose estimation is really also a good example, right? Some kind of the pose, like some rotation and the translation kind of example, the information for the given point cloud is the global information, the per shape, right? For those kind of the cases, we can also consider using this kind of the point entity architectures. But depth estimation, well, I mean, we are having this 3D information, so we don't need to predict depth here, right? Some part of deformation, yeah, it's kind of global, right? If we want to basically somehow deform the point cloud in a way to basically predict some kind of offset for each of the point, then we can also use these kind of architectures for the some kind of to predict the per point information. Autoencoder will be the case that we are having both the encoder and the decoder. So we are not going to discuss the decoder yet. We're going to first discuss the encoder part first. Yeah, so many other kind of examples. Like for example, like we can, if we want to, like given some kind of the geometry information, if we want to predict some texture or some color information for the point, yeah, there might be also the case that we can utilize this kind of like the second architecture, getting some per point information. Right? So basically, yeah, you can think about some lots of the cases, like basically how we can utilize these kind of architectures for many kind of cases. So obviously, like now we are discussing only the architectures that can process the point cloud as the input, right? And making some kind of either some global information or the per point information. And the generation might be the case that we are taking something else as kind of input and then generating the point cloud as the output. So we are not even getting to that point yet. So we are going to first discuss the ideas for the point cloud encoder, and then we're gonna also get into the ideas about the reconstruction of the generation. So basically, if we want to make some autoencoder basically means that we are having the encoder and the decoder. Then this will be the case that we are first basically doing some kind of the compression of the given point cloud into some kind of the low dimensional vector, doing some kind of the compression, encoding the point cloud information into the low dimensional vector. And then we will need to have the decoder, which is now mapping this latent code into the point cloud. So we can also consider lots of kind of ideas for this, like the decoding part. But actually, for the decoding, some simple architecture actually works well. So actually, there is no kind of the complicated things here. But we're gonna also get into the idea of like how we can make some kind of the better decoder for the 3D shapes. And also for the decoding, for the generation, we don't need to use the point cloud, right? So we discussed the pros and the cons of the each of the representation. For the encoding, actually, there are lots of kind of advantages using the point cloud as the input, as I mentioned. Like for any other representation, it's very easy to like convert into the point cloud. But for the generation, we don't need to use the point cloud actually. It's better to use implicit functions. So we're gonna get into that point. Well, yeah, it's considered as encoder. I mean, my point is that if we want to do some generation, we also need to have not only encoder, but also the decoder as well. So we're gonna get into that point later. Ray tracing. Ray tracing is basically the case that we are generating images, not 3D shapes. Yeah. So that's kind of things. Okay, any other questions? Okay. taking way longer time than I expected. So yeah, we will really need to get into some details of the point net next time, and we're gonna continue this discussion next Monday. And please remember that the deadline of the team matching is this Friday. So please submit the team information in the open review, and then I will see you next Monday. You can find all the slides on the course webpage. So if you go to the course webpage, you can see all everything for the slides and the recording, even the recording as well. So you can find that. So I will see you next Monday. Bye.